So this is a very quick rundown in terms of how we've gone about working through this particular problem. So to calculate the safety factor, or the factor of safety, S squared F, that's equal to the ratio of the yield stress to the design stress. We're interested in the design stress, so we make sigma d the subject of the equation, so that'll be equal to sigma y over the factor of safety, or the safety factor. So we're given the yield limit to be 250 MPa, so 250 divided by 2 gives a design limit of 125 MPa. We know what the load on the boat is, so the axial load or the tensile load on the boat is given as 20 kilonewtons. So since sigma is equal to F divided by A, so F is the external load, A is the cross-sectional area, we can then work out the sectional area, and from the sectional area, work out what the diametric span of the boat is. So making A the subject of this relationship, the sectional area is equal to the ratio of the force to the design stress. And if you do the following computation by putting in the known values, we get the sectional area to be approximately equal to 1.6 times 10 to the power minus 4 meter squared. So since we're assuming that, well, we're not really assuming, most boats off shell more or less have a circular cross-sectional profile. So we're going to be using the area of a circle to work out what the diameter is. Now again, as I stated, it's up to you. If you want to use pi r squared and then multiply r by 2 to give you the diameter, feel free to do so. But as you've more or less noticed, I would like to stick with the engineer's formula, which is basically pi over 4 times d squared. So making d the subject of this relationship, we have the following equation, which would be the square root into bracket 4 times the area divided by pi. So we substitute our known variables and we get approximately 14.3. So when we looked at the boat example from the previous chapter, I think that was in chapter 6 for shear stress. So when we're looking at shear stresses, I made a point that it's always best to look at what the nearest dock size is, or the nearest off-shelf size is in terms of boat, because boats are standardized parts. There isn't necessarily a 15 millimeter size bar, not that I can recall, because they normally go up in even numbers from 6 mil. So the nearest bolt size would be 16 millimeters. Okay, so for this particular application, so unless you want to spend a lot of money to customize a boat to a diameter of 14.3, which would be a waste of money, just look for the nearest component size they can get off shelf. Okay, so that's just smart business.
Let's look at situation 2, where we need to calculate the diameter of the boat if we assume that some amount of plastic deformation is taking place within the component during its service life. So we're going to assume that the fill limit is at UTS. And let's not forget that UTS stands for the ultimate tensile stress or strength of the given material. So in this case, the UTS sigma STS is given as 450 MPa. Right? We're still using the same safety factor, so the safety factor for this application is still at 2.0. Okay, so don't forget that I tend to use NS squared F to represent the safety factor. So the design stress so that's sigma D will be equal to sigma UTS divided by the safety factor. Alright, which is equal to 450 divided by 0.0 MPa and that will be equal to 225 MPa. But since we've already worked out how to calculate the diameter, I'm just going to use it straight from the previous example. So for the previous example, this is what we proved, that the required diameter will be equal to the square root of 4 times F, so F is the applied axial load on the boat, divided by pi over sigma d. Pi times sigma d, sorry. So we don't need to use first principles in proving that again. So the diameter required to D will be equal to 4 times F over sigma pi square root. Okay. So again, the applied force is 20,000. And that's being divided by pi times sigma d, which we've calculated to be 225 times 10 to the power of 6 for the square root. All of that. So we'll bring in our trusted calculator again. So we've got 4 times 20,000 divided by into bracket pi times 225 times 10 to the power of 6. And that gives 1.1318 times 10 to the power of 4 into bracket to the power of half, or 0.5, so it means the same thing. And if we do the need a computation, 0.25 for that, that gives approximately 0.0106 meters. It's approximately 10.6 millimeters. So similar to the previous example, if we're going to look for the nearest stock size, assuming that we're not going to be fabricating this fastener to this size, then the next available component, which makes sense in terms of metric sizing for the fastener required to be 12 millimeters. As I stated previously, once we, for metric size fasteners, once we see 5 millimeters, it goes in steps of 2. So you've got 6, 8, 10, 12, 14, and upwards. Okay? And there we have it.
So let's look at situation 2. So this time we're going to work out the size of the boat with respect to the UTF. So similar to what we did previously, safety factor is equal to the ratio of the allowable, the failure limit. So in this concept, the failure limit is at UTS, so that's 450. And we're going to use that information to work out what the allowable design stress is in this context. So sigma d, which is the allowable stress of the design stress, some people would like to call it the working stress. I personally only use the term working stress when I'm looking at assessing components within operational parameters, but when it comes to design, I prefer using the term design or allowable stress. So that will be UTS divided by the safety factor. So 450 divided by 2 gives 225 MPa. So similar to the previous worked out example, we know what the load on the boat is, so that value has been given as 20 kilonewtons. So since we know that the stress is equal to the ratio of the force to the perpendicular, the normal cross-sectional area, then we can make A the subject of this relationship. Thus, the sectional area is equal to the force divided by the design stress, and just by substituting known values, that gives an area of 8.89 times 10 to the power minus 5 meter squared. Okay, so the area here seems to be larger than that of I think it might be smaller. I don't know. We'll come back to that later on when we look at the diametric size of the boat. So, again, pi r squared, up to you, but in this context we're not using pi r squared. We're just going to focus on the engineer's formula. So A is equal to pi d squared over 4. Or if you want to call it pi over 4 times d squared, is up to you. So making the diameter the subject of this relationship, the diameter of the boat will be equal to the square root of 4 times A divided by pi. Do the needed computation, and that gives a value of 10.64 millimeters. Again, don't make the mistake of rounding down. So if you've got 10, you round it down to 8. No, that compromises the safety factor. Okay, so whereas we've used a safety factor of 2, if you round it down to, let's say, 10, 8, you've compromised the safety factor, which is not a good thing. Thus, it's always best to round up to the nearest dot size available. So since bolts do not necessarily come in terms of 11 millimeters, the next available bolt, as I stated, after 6 millimeters, I think after 5 millimeters, everything is more or less manufactured in even numbers. So they come in terms of even number sizes. So the next available ideal bolt size would be 12 millimeters, which not only safeguards the safety factor as specified, but also adds some additional buffer, okay, to ensure that the material operates within its elastic region. All right, so now we've got into different what we call it values. So in the first instance, we got 16, I believe, and in this instance, in terms of the UTS, we've got 12 millimeters. Okay, so why the variation? So the variation is due to the fact that because we want the material to operate within the elastic region in the first instance, the material allowance is going to be greater. Okay, so the greater the material allowance, particularly this cross-sectional profile, the greater the resilience of the material to operate within the yield limit of the material, or below the yield limit of material. The smaller the material variation, the more likely the material is going to deform above the yield limit. And in this instance, the boat has been designed intentionally to undergo or to experience some measure of plastic deformation before eventual failure. Okay. So again, it all comes down to what the designer's intent is. So what is the design intent? What is the intent of the designer in terms of how the material or the component needs to behave during service? Okay. So hopefully we're going to explore more of these situations when it comes to looking at the application of the concepts learnt in future videos to come. So hopefully we've had some flavor in terms of the relevance of the safety factor, or the factor of safety, when it comes to the design of mechanical components with respect to selected or defined engineering material. So as I pointed out, it's very important that we somehow find a way of quantifying these measures of uncertainty that is very difficult to capture when it comes to mechanical design analysis. And this is where the safety factor gives us that guarantee, some measure of guarantee that the operability of the material in terms of how the material is deforming well below the yield limit of the material. Thus, it's operating adequately within the elastic region of the selected material. Thus, when all loads are taken off, the material has time to ideally recover back to its original state. We've also had a look at the indications of selecting the safety factor. So again, the larger the safety factor, the greater the certainty of its operability or its deformation within the elastic region of the material. But there's also an issue in terms of over-engineering the component, thus increasing the material allowance to a state that the component becomes very, very heavy and not ideal for the product. So again, you need to really think about what the trade-off needs to be to get that ideal balance of what the measure of safety factor needs to be to ensure that the component's not being over-engineered. And we looked at 2 examples, so hopefully you were able to follow along through the work along of the given example. So now that we've finished chapter 7, we can now proceed to look at chapter 8. So chapter 8, we're going to be looking at variable loading situations, and there will be subsequent work along problems to complement what we've discussed. And there we have it.
Alright folks, so hopefully everything made sense to you. So any comments that you have, can you just type it down below? And hopefully you join me in the next session. So please share and subscribe, and I'll catch you in the next section. Bye for now.